Here we go. All right, so today we're going to get to one of the kind of main ideas in this course, which is should, I think, be new to you, and that is the notion of an affine connection, and then we will build to see how it's useful in talking about mechanical systems. Okay, so affine connections. Okay, so an affine connection is an operation which takes two vector fields and produces another vector field, and it does so in accordance with certain rules. So it's just one of those kinds of things, and so it needs one of these. Okay, so let's let M be smooth manifold. Okay, so an affine connection on M is a mapping and what it does is it takes as its argument two vector fields x and y. Okay, so these are vector fields, as I'll say in a second. And it produces another vector field, and the symbol we use for that looks like the symbol you might have used as like the gradient operator in vector calculus, but this isn't the gradient operator. It's a differentiation kind of a thing, as we'll see. So that's why it's not ridiculous that it have a piece of notation attached to it that looks like something you've seen previously as a derivative. But this is not the gradient, and the way that you pronounce this in English is you say nabla. That's N-A-B-L-A, nabla. In LaTeX, \nabla. Okay, so that's what an affine connection is, and so what it returns for you is it returns for you a vector field. Okay, so a smooth vector field, and its arguments are vector fields. Okay, and it has to satisfy some conditions, of course, and those conditions are the following. And first of all, the mapping is bilinear. Okay, and when I say R bilinear, this is making reference to some of the things that we talked about last time with respect to the various kinds of algebraic structures on spaces of functions and vector fields. And so what we saw last time was that the space of smooth vector fields has the structure of a vector space. Okay, and so then you have addition and scalar multiplication, and it's that I'm talking about here. So real scalar multiplication, because the space of vector fields also has a multiplication by functions. If you take a vector field x and you multiply it by a function, you can make sense of that as a vector field. Okay, and so when I say linear bilinearity here, I mean that it's linear in each of its arguments with respect to scalar multiplication, not function multiplication. Because with respect to function multiplication, it has its own different set of rules that are important. Okay, and those are part of the definition. Okay, so if you multiply x by a function, okay, so we saw what that meant last time, then it's linear with respect to function multiplication in that argument. Okay, and this is true for all functions f. and all vector fields x and y. Okay. And then you also can ask what's the function multiplication operation in the second argument, y. Okay, and as I said, you know, the nabla suggests that there's some kind of differentiation going on here, and there is. And so if you think about what kind of rule should be satisfied by a multiplication like this, where you have two functions of x, f and y, you expect that the multiplications should satisfy the product rule in some way. Okay, and so the idea should be that the derivative of this thing should be this times the derivative of that, okay, plus that times the derivative of this. And so it's just a question of making sense out of what times means. And if you think about it for a second, there's only one way to do that. Okay, so first we're going to fix f and then differentiate with respect to y. Okay, then we're going to fix y and we're going to differentiate with respect to x. Okay, so we're going to differentiate the function f with respect to the vector field x, but we saw how to do that last time, and we called that the Lie derivative of f with respect to x. And the notation we use for that was like this. Okay, and again, this is true for every f, a smooth function, and vector fields x and y. Okay, so those are the rules. So, you know, okay, whatever. Unless there's some particular interesting thing that happens because of those rules, then it's not necessarily interesting, but of course there is, or else we wouldn't be talking about it. All right, so let's see what these things actually look like. Okay, and in this course, when we try to understand what something looks like, what that means is we try to represent it in coordinates. Okay. All right, so let's look at the coordinate representation of an affine connection. Okay. So in other words, you know, what is that thing? What does it look like when you write it down in coordinates? Okay. All right. So what you do is you choose coordinates. X, little x for m. And then you take your two things you know about, which are x and y, and you write those in coordinates. So that means x is xj d by dxj, and y is yj d by d. Well, maybe not. Let me not d by d xk. All right. All right, then what I'm going to do is I'm just going to sort of write this thing down, okay, and then start applying the rules, okay, and see what pops out basically. Okay. So then we calculate. Okay, so nabla x, y. All right, so x and y, we're going to write as linear combinations of these basis vector fields, and we're going to plug that in there. So it's going to be nabla xj e by d xj. And then up here, I'm going to get the vector field, and I shouldn't use j, of course, so I'll use k d by d xk. All right. Okay, and so you can see now how the rules are going to show up here. Okay, because what I've done in for both x and y is I've written them as functions, namely the components, times the basis vector fields. Okay, so these xj's and yks are functions, and these are the basis vector fields. Okay, so you know, our operations up here tell us how to work out what happens with an affine connection when we multiply vector fields by functions. So we're just going to apply the rules. Okay, and we're also going to be just implicitly using the linearity with respect to addition and scalar multiplication as well. Okay. All right, so let's first expand with respect to x. Okay, now, so x has this function times this vector field, and we know that that's particularly simple. The function just pulls out front. Okay, so first we get xj nabla d by dxj, and then we get, so I could expand that, but let me just do it slowly. Okay, so I get yk d by dyk. All right. Okay, so now I'm going to now use the third condition here, because now I have a function times a vector field. Okay, so I have the function yk, the function yk times the vector field d by dyk. So I'm going to apply the rules. Okay, so it's going to be xj times. All right, so the first is I pull the y out front, okay, like here. All right, so it's nabla d by, sorry, pull the y out front like I said I was going to do. Yk nabla d by dxj d by dxk. All right, so that's holding this fixed, holding this fixed and then differentiating that. Okay, so that's what this is. All right, now what I need to do is I need to hold this fixed, okay, and then differentiate y. Okay, and what am I going to be differentiating y with respect to? I'm going to be differentiating with respect to that vector field. Okay, just like in condition 3. Okay, I hold the vector field constant and I differentiate the function times the vector field x. Okay, so the vector field x is d by dxj and the function is yk. All right, so good. Let me just stop talking about it and do it. Okay, so differentiating yk with respect to d by dxj gives me d y k by dxj, right? And then it's d by dyk. All right, so that's literally just an application of the rules of how you manipulate affine connections. Okay. All right. Okay. Now, so I know what all of this stuff is. All of this kind of makes sense to me. That's just, you know, some expression involving derivatives. The only thing that doesn't make sense to me now is that thing. What's that? Well, the fact is that that is what it is, which is, you don't really know what it is. All you know is that because nabla is an affine connection, you know that that thing is a vector field. That's all you know, right? Because it takes the two vector fields d by dxj and d by dyk, and it gives you some other vector field, okay? And so that's all you get to do at this point. And so nabla d by dxj d by dyk, sorry, not yk, xk is a vector field. Therefore, it's going to be a linear combination of the basis vector fields. Okay, and there's going to be some coefficients in that linear combination, and we don't know what they are. They're given to us by the affine connection. Okay, so there's going to be some, yeah. Sorry, which ones? Oh, I apologize. That's just because I screwed up. Thanks. Yeah. Is that was your question? That it was the X's that you wanted there? That was your question? Yeah. Yeah. Sorry. Thank you. Okay. Okay. Okay, so I have some coefficients in this linear combination, and I'm going to call those gamma. Okay, so I need to, gamma will have an elf component, so gamma L. But then I know also the gamma is going to depend on J and K, because it depends on which basis vector fields I plug in here. And so I get a J and a K there. All right. Okay, so I know that that's going to be true for some of functions gamma. Okay, and this is for some functions gamma L J K on the domain of the coordinate chart. Okay, so having now written that, okay, let me rewrite what I had up here. Okay, so then nabla x y is, okay, and now I'm going to relabel some indices here so that I can pull a basis vector field out front. Okay, so I'm going to call this K, I'm going to call it L so that it matches that one. Okay, so it's going to be d y L by d x j. Okay, x j plus gamma L j k x j y k d by d x L. Okay, so that's it. That's as good as you get. And so what you see, one of the observations that comes out of this is there's a thing, these gammas, which you can't reduce to some other known thing about manifolds, right? It's not the derivative of something with respect to something else. It's just they are what they are. And so these are what are called the Christoffel symbols of the affine connection nabla in this set of coordinates. Okay, so the functions gamma L J K are the Christoffel symbols for nabla in the coordinates okay. All right. Okay, so the point is, if prescribing an affine connection is somehow the same thing as telling me what these functions gamma, the Christoffel symbols, are in any set of coordinates. Now, there should be an alarm bell ringing in your head here, because there's possibly a problem with that, right? Just in the same way that prescribing a vector field, okay, is somehow the same thing as describing the components of the vector field. Well, that's subject to the condition that those components that you gave me satisfy the transformation rule for vector fields. Okay, and so there has to therefore be a transformation rule for Christoffel symbols that you can go off and check to make sure that if you give me two overlapping charts, okay, and Christoffel symbols here and Christoffel symbols here, the resulting thing on the overlap of those charts is such that those are the Christoffel symbols for the same affine connection. Okay, so Christoffel symbols have their own transformation rule, and it's messy. I might be able to remember it, but I don't want to, because it doesn't matter for the purposes of this course. But I do want to mention that there is such a thing, and that these gammas can't just be arbitrarily specified. They have to satisfy transformation rule, just in the same way that vector fields and co-vector fields, etc., have to satisfy transformation rules. Okay, so I'll just summarize that as follows. And the transformation rule for Christoffel symbols is given in the course text. And if you look at that, so I encourage you to maybe go and look at it, because the transformation rule for Christoffel symbols looks quite a lot like the transformation rule for accelerations that you have in a homework problem, right? If you take x double dot of t, and then try to figure out how that changes coordinates, it looks a lot like the Christoffel symbols. And there's a reason for that. So there is a transformation rule for Christoffel symbols to ensure that on overlapping charts, two sets of Christoffel symbols come from the same affine connection. Okay, so there exists such a thing, and like I said, I'm not going to write it down. Okay. All right, so I use this symbol gamma, okay, not by mistake. You remember when we derived the Euler-Lagrange equations for the kinetic energy Lagrangian, there occurred a long messy expression, which we're going to be writing down again shortly, which came out of the Euler-Lagrange equations, and I wrote that as gamma with a g on top. And I told you that those were Christoffel symbols for a particular affine connection. Okay, and so we're beginning to work our way towards understanding what those things are. Okay, but before we get to that, let's maybe take a look. Actually, no, let me get to that right now. There's nothing to stop us from doing that. Okay, fact. There is a deep connection between Riemannian metrics, for example, the kinetic energy metric on a configuration manifold, and affine connections. Okay, and so there's these group of characters whose names keep coming up here: Riemann, Christoffel, Levi-Civita. These are all people who were there at the founding of this subject in the latter part of the 1800s and the early part of the 1900s. Okay. And this connection is given to us by what's known as the fundamental theorem of Riemannian geometry. Okay, and the theorem reads like this. For a Riemannian metric, G, there exists a unique affine connection nabla with a G on top. Okay, and this is called the Levi-Civita. So Levi-Civita, by the way, is one name, Tullio Levi-Civita. Okay, satisfying two conditions. Okay, so here are the conditions. So the first condition, so I'll write it down and then I'll tell you how you should understand what that condition means. Okay, the first condition says let's take a function, and the function is going to be defined as follows: take the Riemannian metric G, evaluate it on two vector fields x and y. Okay. Now, G is an inner product on each tangent space, right? So if you give it two arguments like x and y, at each point, it gives you a number, okay? So therefore, that thing, G of x, y, that's a function, okay, on M. And as a function, therefore, I can differentiate it with respect to another vector field, okay? And I will do that. Okay, so I'm going to go LZ, okay? So this thing is a function. Okay, and so LZ means the Lie derivative of that function with respect to the vector field Z. Okay, and that should satisfy a formula like this. Okay, all right, so that's the formula. So let me explain to you now how you should understand what that formula means. Okay. So on this side of the formula, I have this function, but this function somehow is really a product of three functions, right? So it has three things that are participating in it: x, y, and g, right? And all of those things vary as x varies. Okay, so what you anticipate then is if you differentiate something like that, you should end up with, by some kind of a product rule, you should end up with three terms, right? You're going to get a term that involves fixing these and differentiating that, fixing that and differentiating that, and then fixing that and differentiating that. Okay, now look on this side. Okay, what do we have on this side? Well, on this side we have two terms, not three. Okay, but the two terms that are there are recognizable in terms of the kind of operation that I just talked about. This term, okay, evidently what I've done is I've fixed that and I fixed that, and now I'm differentiating this with respect to Z, right? That's right. And because when you take a look at this formula for the affine connection in coordinates, there's a differentiation going on here. Right, there's a differentiation of y with respect to x. All right. Okay, so this is this involves fixing g and y and differentiating x, and then similarly, this term involves fixing g and x and then differentiating y. All right. So the term that's missing is the term which might look something like this. Okay, so I'm going to write it in red because it actually isn't there. Okay, so the term that's missing is nabla g, okay, of x, y, right? Now, I haven't exactly told you what nabla g is, okay? So somehow, sorry, I apologize, that the g shouldn't be a subscript like that. That should be nabla z, g, okay? So I haven't told you what that thing is, so it's fortuitous that we don't need it. Okay, but somehow there's a way of differentiating g with respect to z. Okay, so let's just forget about exactly what that is, but let's just understand that that term is differentiating a g with respect to z. Okay, and what this says is that that derivative is 0. Okay, and so the way to read condition 1 is condition 1 says that the derivative of g with respect to the affine connection nabla G is 0. Okay, and so the fact that this thing is 0 means that, and so I'm speaking very loosely here, so it means that the derivative of G with respect to nabla G is 0. Okay, so that's how to read condition 1. Okay. All right, yes.
Yeah, so this is change another con. It's not
Yeah.
Oh, sorry, it doesn't show up there? Or it doesn't show up very well. I can sort of see. Yeah, sorry about that. I don't know if there's a way to globally, if there's a way to change the color afterwards. But so I'll just rewrite it. Sorry. Thanks for telling me after I got it all down, by the way. So let me know if yellow works. How's that? Okay. All right. No problem. So sorry. So I didn't want to write that. So the term that's missing here, as I said, is this nabla Z G G. Okay, of X and Y. Okay, so this term is the one that's not there, and so this thing is being equal to 0 implies that again the derivative of G with respect to nabla G is 0. Okay, and so again, the full product rule you would expect to kind of look like that, but the missing term should be interpreted in this way. Okay, all right, good. So that's a condition 1 of the definition of the Levi-Civita connection. Condition 2 reads like this. Condition 1 in some ways is the most important one. And condition 2, what it really does is it turns out that, and we'll kind of see why, it turns out that there's a bunch of affine connections that satisfy condition 1, but they all differ in only an uninteresting way. And condition 2 fixes one of those possibilities for all the things that satisfy condition 1. And so the condition reads like this. I'll write it down and then I'll explain to you how to understand what that means. Okay, so that's the condition. And so this involves the Lie bracket of 2 vector fields that we talked about last time. And so involves the difference of the affine connection applied to X and Y and X. Okay. All right. So condition 1 I've interpreted. Condition 2. This condition means that the Christoffel symbols and I call these Christoffel symbols specifically nabla G, gamma G, L, J, K, okay, satisfy that they're symmetric with respect to J and K. Okay, so okay. So if you write that condition down, that's exactly what it means. So I think last time I maybe forgot to tell you what the coordinate formula is for the Lie bracket. So to verify that this implies that you can use the coordinate formula for the Lie bracket. Okay. So let me not do that. Okay. So to understand two, okay, we use the coordinate formula for the bracket, which I'll write down. Okay, and so maybe while we're here, sorry, I'll be right back to that, but let me, because I think it's interesting to compare these two formulas. Oops, matter, hopefully. Here, let me, I still have it in the buffer. Yep. Okay, let's take a look at these two formulas and see how they differ. Somehow both of them can be thought of as being differentiation, right? Let's maybe think in both cases of x as being fixed, okay? And so if x is fixed, okay, you can see here, and in fact, sometimes this formula, because you can think of it as being a derivative of, say, y with respect to x, sometimes this thing is actually written as lxy, okay? But it has a property of differentiation with respect to y, which is not necessarily that pleasant, and that is because it also involves derivatives of x, okay? So it does differentiate y, okay, here, all right, but it does so at the cost of also differentiating the thing with the thing which with respect to your differentiating, okay? And so one way, not necessarily the best way, but one way to think of nabla is that it gives you a way of differentiating a vector field y with respect to vector field x without also having to differentiate x itself, okay? Because you notice here that x appears without any derivatives in front of it, okay? So this just makes you think, why not just do this then? Oh, sorry. Right there, I've differentiated y with respect to x without having to differentiate x. What do you think might go wrong with a formula like that? That formula makes no sense, I claim. What is there that may be wrong with that formula? Well, what kind of an object is this? It's a vector field, right? Therefore, it has to satisfy the transformation rule, okay? But you can work out the transformation rule for that, right? Because you know what the transformation rule is for vector fields, and that thing does not satisfy the transformation rule for vector fields, okay? So this is poppycock, okay? Because it doesn't satisfy the transformation rule. How's blue, by the way? Is it okay? Better than red? Okay. Okay, good. All right. Okay, so and so the way that you can get around this to define a differentiation of a vector field with respect to another vector field that doesn't involve the differentiation of the thing you're differentiating with respect to, that's one way to think about what an affine connection does. Okay, and in fact, this nabla xy is called the covariant derivative of y with respect to x. Okay. All right, so sorry, I got sidetracked there when I wrote down the formula of the Lie bracket, because what I was actually trying to do there was I was trying to explain that if you have this formula for the Lie bracket and then you write down that equation, okay, you will see that that equation implies directly that. Okay, that was the point of actually writing down the formula for the Lie bracket. But then I just couldn't help myself from pointing out the comparison to that. Okay. All right, so so maybe for the sake of organization, let me put all this as an aside. An interesting aside, but still an aside for the purposes of what I'm talking about. Okay. Because what I'm really talking about is the Levi-Civita connection. Okay, and so one can verify from conditions 1 and 2 for the Levi-Civita connection, nabla G, that the Christoffel symbols are given by exactly the thing that we derived when we derived the Euler-Lagrange equations. Okay. All right, so that kind of, in some way, closes the loop a little bit on where we ended up when we talked about the Euler-Lagrange equations for the kinetic energy Lagrangian, because I've kind of told you at least now of what those gammas meant that showed up in that formula. Okay, and so remember, just to solidify this, since it's been a while since we talked about it, so recall that the Euler-Lagrange equations for the kinetic energy Lagrangian were exactly x double dot L plus gamma G L J K x dot J x dot K equals 0. Okay, so they were second order differential equations, and they directly involve these Christoffel symbols for the Levi-Civita affine connection. Okay. All right, now, so what we want to do now is, okay, so we've identified what these Christoffel symbols are, okay, but is this whole equation, okay, is that something? Okay, so in other words, is there an affine connection-y thing, okay, for which when you write it in coordinates, it looks like that? Okay, and the answer, of course, is yes. And so we're going to start to introduce that, but I have 5 minutes to do something that I will just have to reproduce at the beginning of next lecture. So we're going to stop there today.